right, thanks. So I'm here today to talk about, I committed when the abstracts went in to say I'm about to do a circle and I'm going to tell you what happened. So I'm going to do that for a little bit and then I'm going to talk about where I thought things might go. So, okay. So it started with me teaching numerical analysis. This is sort of ridiculous thing in my magnet high school class, which has extremely advanced students. And one of the standard topics is interpolate a polynomial given some number of points. And so meanwhile, I'm working on planning a teacher circle and leading a student circle, and I said, okay, I can use this. So, so there's a lot of interesting aspects to this, and in the end, what people learn is this Newton divided difference table. A lot of people don't learn it anymore, but this is the whole topic. And this does seem to have made its way in a cartoon version to the high school curriculum. So in the warm-ups for my teacher circle, all my teachers knew that if you take values of a polynomial function and start differencing, then if you get a constant and then 0, then it was a polynomial of degree n if it took you that many differences. And I turned to them and said, so why is this true? Total blank. Okay, so the strategy is to try to explain that and many other things, and essentially it's an entree. I'm a great calculus lover, so it's essentially an entree to discrete calculus. And then many people don't learn Newton's version, but learn Lagrange's version, which is essentially find the dual basis, so you can just write down the solution. It has some pros and cons, especially on the numerical side. It's not particularly useful. And so in the end, I was rethinking Newton's polynomial interpolation as basically being a recursive algorithm. And this boils down to the most basic facts that students learn in high school algebra. Maybe not the most basic, but one of, which is p of x minus p of a is divisible by x minus a. So how did I try to, so my crazy goal was to try to get the students to rediscover this formula of Newton. And then I would have them, what was brought up yesterday by Dan, we'd have a yaw moment and they'd say, hey, cool, you guys just did what Newton did. Okay, but we'll see if it didn't quite go that way. So what I thought at the start was get students warmed up or whatever. We had a game where we would sort of guess my polynomial, and the only thing well, there were some rules. The students made the rules of what degree and how big could the coefficients be, and the only thing you got was to query the student who made up the polynomial. I tell you x, you tell me p of x. So I thought this was a beautiful setup, and I assumed that, well, so this turned out to be harder for them than I thought. I thought they would just ace this really fast. So one of the things I'm learning as you run circles is you can plan and then things happen. So, okay, so I thought they'd be pretty fast, and eventually we would get to the key questions, which are how many values are the minimal number you need, and if you have the minimal number, what do you do? So that was where I thought we'd be. My older kids who were more experienced eventually kept going to the standard basis, 1x, x squared, and find the coefficients. So they were very boxed into, if you hand me a polynomial, it is, you know, if it's quadratic, ax squared plus bx plus c. It only comes that way. Or maybe it comes factored. But the whole idea of the Newton thing is to write it in this nested form. Okay, so eventually they came to this van der Laan determinant, that's the classical algebra thing, and then they couldn't quite figure out what that why that determinant was 0. That's, okay. And they never hit on the recursive.
I'm sorry, can you, I don't know the term van der Laan matrix.
Okay, so I'm going to be short for time. Let me just say it's a matrix that has, as its row, let's say 1, and then x sub j for each of the interpolation, and then xj squared, xj cubed. Okay, so it's the system of equations you get for trying to solve for the coefficients. And then it's a fun algebra exercise to decide what that is. And there's also interesting history of math of why van der Laan was doing that, but that's a different talk. Okay, so was this a success session? So I'm going to spend only a little time in the session, and then I'm going to say where I thought things might go as a much more extended narrative. And then I really want some feedback from you all about how to make this work better the next time I try it. Okay. So they did have fun. They were trying things they were thinking, but they didn't really get to this deeper math. I lack Jim's ability to get the kids to just get there. Okay, so there were some other things I thought might emerge. One of these is if one of the rules they made up was that their polynomials had to be factorable over the integers with small size when they were trying to play the game. So that should mean that students should be able to just experiment and find the factors. This drives me nuts because students try to memorize factorization. They learn this rational roots thing. They don't understand it. But if you use your common sense and think, if you had 4x squared plus bx plus c, then one of the factors, it's either 4, 1 or 2, 2. Just run some numbers, factor them, and look how the factors grow. Sort of end of discussion. Okay, but that's not what anybody does. Okay, so schools and rational roots is kind of done down. So when I tried to anticipate where we might go, there were all kinds of things. All right. So the idea for the Newton one is if I have p of x and you tell me the value of x equals a, then I can always write this little equation. We use this equation all over the place in math, right? Triangle inequality for all us analysts, all kinds of other things. And so Newton's interpolation becomes this nested or recursive solution. So if I know the value at x1, then p of x minus x1 has an x minus x1 factor. And the nice part about this is the quantity you get is the difference quotient, which we end up in calculus spending a lot of time talking about. Its limits, but for polynomials, the limit problem is trivial, and that's nice. So, okay, so we write this, and then we look at the values of P1. And P1 is this difference across the points. Now, the classical Newton interpolation table doesn't do it this way. It takes the x values, and then the y values, and then does differences of neighbors. This one said this is the recursive variant, chose my first point, and now run with it. Okay, so if you do it again, which the computer science folks like to do, right? Did it once, do it again, it's recursive. So now I get this nested second one, and P12 is the difference of the differences, so it's a second difference. Okay, and now it's an easier interpolation problem, so I'm always going down a degree, so I can just keep going. Okay, so this gives me a nice nested form of the solution. There's all kinds of good questions that pop up. For example, I chose a particular ordering of the points, but the interpolation problem is independent of the ordering, so I have some nice combinatorics questions. It's also a nice thing for linear algebra preview that here's a different basis for the family of polynomials, and in this case it's much more valuable. And then there's a numerical component of nested multiplication is the smart way to evaluate polynomials on a computer. Okay. So, all right, so I probably just said everything on that slide. The usual divided difference table only shows some of the differences. And then if you play a little, you say, well, do the recursive thing, but do it at the same point. That's now Taylor polynomial of a polynomial, right? Every calculus teacher's trick question. What's the remainder? And you do a polynomial interpolated polynomial approximation of a polynomial. Okay, but now there's other kinds of questions. So you can go to this p of x minus 1 and start playing, or you can do it. So just so we're clear, here's x cubed, which like a typical early high school kid could do. X cubed minus 1, peel off the x minus 1, and then you get this nice thing that you have the sum of all the previous powers, and those guys all have factors, and if you do this, you basically prove, you can turn this into a proof of the binomial theorem, sort of barehanded. The only thing you do is divide, and go. Okay. So that's fine. It also, so other aspects of this, we end up with the secant line. We actually can prove this bad high school description of differencing leads to the degree of the polynomial. Okay, and there's also alternate questions. So this is where I was more excited. What if the power is -1? Or what if it's the square root? Or what if it's some hidden function f of x? Okay, so essentially the theme of calculus is that for differentiable functions, f of x minus f of a is divisible by x minus a. Right? And for those of us who teach advanced calc and proofs of calculus, that's really big. You could also start saying, well, the algebra, one of the things they sneak by students in algebra pretty quickly is going from reals to complex numbers, right? This discriminant enters and all of a sudden it's fine. I've yet to see a high school math book that talks carefully about complex roots means the polynomial's complex value. That means we changed the domain. We did something really sneaky. Okay, so I kind of contemplate a session if I had Josh's ability to lead one of these where I would just say, hey, p of x minus p of a is divisible by x minus a. Do something. Okay, but, well, we'll see. I may get that ambitious. Okay, so here's, for example, 1 over x, which is very cute. So if you take 1 over x and you do this peeling off, that's those of us who do this algebra and calculus know, you get back a 1 over x. Well, we're doing recursion, so go for it. Okay, so you end up with an infinite sum. Purely algebraically, it's of course a geometric series, but we know other things, but just as an algebra problem, it just goes. Sort of Eulerian style. Okay, if you have 1 over x squared, then you get a 1 over x squared, but also a 1 over x. Kind of the flipped version of when we did x cubed and we had x squared. So on. So with a little more facility, or fortitude, or whatever, you end up with another famous series pretty easily. And all you've done is divide infinite many times. Okay. And then if you're trying to set them up for calculus, which would be maybe my bias, you can start doing things like the -1 power of p of x. Right? So forget 1 over x is a special case. You get a recursive thing. Strangely, it involves the difference of original p in the denominator now, and so you can keep going. Okay? You could do the discrete product rule. Not so symmetrical. We all know that when we teach it. Well, those of us who teach calculus. Okay? You could do the quotient rule. I apologize, I'm kind of flying through the slides, but time is rapidly going by anyway. And most fun, you could do the chain rule. All right? So if you have a polynomial p, and you take a polynomial and another q, and you take p of q of x, that's a polynomial. Not fun to calculate. Well, you don't want to expand it. That's a good thing for the chain rule in calculus and composite function scheme. But if you start doing the dividing, you rapidly figure out that the quotient, right, involves both quotients in the chain rule. And when you teach things like when I teach complex analysis in the high school, which is another crazy thing, or advanced calc for complex at the college, you end up trying, some people prove the chain rule by this multiplicative style, right? And the point is differentiability makes corresponding differences continuous. Okay, so you can sort of set students up. So I was, in my ambitious life, I can think of all these things, the 1/2 power, the -1/2 power that you get coming back off of that is a little harder. So this one pushes your algebraic calculation a bit. But you can pick up the idea that if you switch gears, which came up in Parry's talk, right, the square root versus the square, you can do it in the inverse function. That looks a lot like derivative of an inverse function. Okay. Many high school algebra books set students up for calculus. They try to do partial fractions. Again, it's sort of, here's some equations, grind them out. If you think about the divisibility, it goes much nicer. So this one's kind of cute. If you had 2 roots, I'm sticking with 1. And then partial fractions emerge nicely. If you keep going, okay, so Excellent, which is good. Okay, so what happened in the session? Well, my students they were much happier to have a concrete problem, and they're more prone to be contest type students. They love contest problems. They're willing to dive in. But if you sort of set them loose to develop a more theoretical framework, we still have a ways to go, although that's fun. So they do like the examples. Okay, as leader of this, I'm still trying to figure out how to do this. I don't really understand how to do it well. So there's some delicate balance between leading questions and giving time for the students to just do what they need to do. Okay, so one of the big decisions, like in this thing, is an activity, is do you start with a numerical value for the other guy, or do you start calling it A or X1 or something? Do you do general polynomials? Do you do specific ones, powers, so on? Where do you put them? Very happy to have advice from anyone who understands this better than me. And the key thing I think about the math circle stuff is I really think it's like improv or something. You're standing there, you think you know where you're going. They might go there, they might go somewhere else. And so it's not the easiest thing to lead, but then again, one of my friends who was a professor at the University of Kentucky once said, a successful lecture is when you've done no permanent damage. And so, in that context, leading a math circle, it's hard to actually do permanent damage. So you should just go ahead and enjoy it. And so, and I really would welcome any feedback on anyone who tries any variant of this and does it well. And I'm hoping to write up some set of things for the general repository of circle ideas. So thanks and great. Any questions?